Dr.A.Vaniprabha, Associate Professor, EC Department, working in SNS College of Technology. Today our lecture series is about signals and system. In the previous lecture, we have discussed about the definition of signal, the classification of signals, and some problems related to the determination of energy or power, periodic or non-periodic, even or odd signal. In continuation with the previous series, today we are going to discuss about further classification of signals like analog and digital signals. What is an analog signal? Any signal which is continuous in nature with respect to time change, it is called as an analog signal. Whether digital signal is extracted from analog signal? Yes, of course. It is a kind of representation of a signal with respect to discrete periodic time intervals. How to get a discrete time signal? It is obtained by a method called sampling. So once the analog signal or continuous time signal is sampled at regular time intervals, we can get a discrete time signal. So these are the samples of the continuous time signals. This picture represents the continuous time signal and discrete time signal and digital signals. Next is the basic operations on a signal. What are the major operations that can be performed on a particular signal is, as we do regular operations in mathematics, the same shall be achieved here also. That is scaling, addition, subtraction, shifting, and reflection, everything. So what is scaling? Scaling is nothing but either increasing or decreasing to a certain amount of value. Amplitude scaling. In this operation, the amplitude of the given signal is either scaled up or scaled down. For example, y of t is equal to x of t is the actual signal, whereas if the amplitude has to be scaled means y of t must be equal to some times of x of t. Alpha shall be represented as the multiplicative constant. It can be either greater than 1 or less than 1. So based on the value of the alpha or the coefficient of x of t, the resultant signal varies. The same is for discrete time signal also. Y of n is equal to alpha times of x of n. And next is addition of signals. Addition of signals, as the name implies, it is the resultant of the summation of two signals. For example, y of t is equal to x1 of t plus x2 of t. And similarly, if it is a discrete time signal, y of n is equal to x1 of n and x2 of n. And multiplication. Multiplication is also the product of two different signals. Y of t is equal to x1 of t and x2 of t. And similarly for discrete case also, differentiation is applicable only for continuous time signal, whereas why? Because the differentiation is done with respect to change in time, whereas in discrete time signal we can't have a continuous change over the time axis, therefore that is not applicable for discrete time signal. And similarly integration also, y of t is integral limit lower to upper limit the function x of t dt, whereas this is not applicable in the case of discrete time signal. Next is time scaling. As we did for amplitude scaling, the same concept applies here. Unlike the coefficient of x of t, here t has a coefficient like y of t is equal to x of alpha t or beta t. This alpha represents the multiplicative factor This alpha can either be less than 1 or greater than 1. Next is reflection or mirror. Reflection is nothing but the mirrored signal, like y of t is equal to x of minus t, or y of n is equal to x of minus n. So this minus represents the opposite axis, hence it is named as mirror signal or reflection. Next is time shifting. As the name implies, shifting in the time axis, right? It can be either x of t plus t naught or x of t minus t naught. This t naught represents the amount of time it has to be, the original signal has to be shifted either to the right or to the left. If the time shift is greater than 0, t naught is greater than 0, then it moves towards right shift, and if it is less than 0, it moves towards left shift. So that is the same for a discrete time also. For example, y of n is equal to x of n minus n naught, where n naught represents the time shift, amount of time shift. If the n naught is greater than 0, then the signal is completely shifted towards right side, and if it is less than 0, the original signal x of t will be shifted towards the left side. Then see here, in this given example, y of t is equal to x of at minus t naught. So here in this expression we can observe there is a scaling in the t-axis and also shifting. Both has been done here, time shifting along with the time scaling. So this is about the basic operation of signal. The major operations of signal are, one is amplitude scaling, next is addition, multiplication, differentiation, integration, time scaling, and reflection, time shifting, and combination of both. These are the major operations that can be performed on a signal wherever it is required. For example, let us understand the concept of time shifting and time scaling by using this example. Consider y of t is equal to x of 2t plus 3. Right? Okay. So how this new y of t can be achieved? With the given original signal x of t. X of t is given as a rectangular signal that ranges from minus 1 to plus 1, having an amplitude of 1. Okay. Now we can do the scaling and shifting operation one by one. So here the original signal is x of t, which extends from minus 1 to plus 1. First, the scaling operation shall be done. The scaling is done in time axis. It is 2t, 2 times of t. If t is greater than 1, then the time or the signal will be reduced. As we use in a normal graph sheet, if we maximize every unit with a higher value, then the final diagram will be compressed or become smaller. The same happens here too. If the time axis is divided by 2, then it gets reduced by minus 1 by 2 to plus 1 by 2. So this is the time scaling. Then next comes to time shifting. If the shifting parameter or shifted time parameter is greater than 1, then what happens? So we can understand the upper limit and lower limit of the rectangular signal here. It is minus half to plus half. So therefore take one end and you operate it with the 3. So half minus 3, which gives minus 2.5. Again here minus half minus 3, then it is minus 4.5. So this is the time scaling and shifting operation. Hope you can understand this example better. Next comes the topic of elementary signals, or the other name of elementary signals is standard signals or basic signals. There are many types of basic signals like exponential, sinusoidal, unit step function, unit impulse, unit ramp, rectangular, triangular. All these are the exponential signals or elementary signals. So how to represent an exponential signal? X of t is equal to e power minus at. If the exponential power is minus a, then the resultant signal is decaying signal. If it is plus a, then the resultant signal is a rising exponential. If it is equal to 0, then it is a constant value. What about sinusoidal signal? We know x of t can be represented as a sine omega t or a cos omega t plus theta. So this is the representation of sinusoidal signal. What about step function? It is represented as u of t is equal to 1 for t greater than 0. So for the condition whenever t is greater than 0, always u of t is equal to 1. It is always high logic. As we switch on, then the light is continuously in on state. The best example for step function is switch on and off. Next is unit impulse. Unit impulse is the case in which the output del of t is always equal to 1 only at t is equal to 0, or del of n is equal to 1 only at n is equal to 0. In other cases it is non 0. Next is unit ramp function. It is represented as r of t. R of t is equal to t for all the values t greater than 0, and it is equal to 0 for t less than 0. So hope you understood the basic operation of signals and standard signals what we discussed today. The rest we'll discuss in the next class. Thank you for listening. Hope you understood this session. Thank you.